To introduce myself, as I did that yesterday, but I'm going to be talking a little bit about new technologies, or probably more in general, post-harvest technologies, of which some can be applied to the ripening of commodities. But I try to at least describe, the overall components of, or generalities of the technologies, basically so that you guys can start brainstorming what are your needs, what are your requirements, how can the current technology help you better your ripening conditions and or your post-harvest quality or the product being offered to the consumers, and basically so that you can also start thinking what is not available, what is not out there, and what do I need to be able to make this better. So this is just a very simple description of the different processes that you can observe from producers to consumers, and what are some of the reasons of why we see food waste and food loss. Basically, I was hearing right now that food waste and food loss is a big concern for the majority of us. We can agree on this, and it actually is. As you can see in this graph here, I've tried to divide both food loss and food waste. And let me specify what I mean by food loss and food waste. Food loss is food loss is basically when it's been during production or processing, when you're disposing of product during production and processing, and food waste is discarded after it's in the market or during the consumers. Interesting enough, we could look at this figure in detail, but in average, we can say that around 45% of the food in the world is either wasted or lost. And it is the same in developing as in non-developed countries. In non-developed countries, food waste is almost undetectable or to the minimum, but food loss is very high. And developed countries, and this is a graph of the US, food loss is at the minimum. And why is that? It's because we have available technologies that help us take decisions and help us reduce the loss of produce. But food waste is exponential, so it's very, very large. And this is important because, as you can see here, where I'm saying like 1/10 of the energy, half of the land, and 4/5 of water in the United States is used for getting food to consumers, but nearly half of the food is being lost and or wasted. This takes us to a different statistic. As you say, for every 12 calories we put into the food system, actually 1 make it to the consumer. And the question at the end of the day is, how can we improve this? How can we make this better? How can we offer safer, better quality products? One avenue is through technology. For me, and I work in post-harvest, so I'm probably biased, but one of the inventions of the 20th century that brought us to where we are today is refrigeration. As you can see here in the x-axis, we have millions of years of Earth or whatever, and then how exponentially after the introduction of technology and engineering and food science, how the population of the Earth dramatically increased. And that's because we could offer better products, safer products to the rest of the world, in addition of many other factors, but that's one. And in the post-harvest systems engineering, which includes, in this case, ripening rooms and equipment and so on that we described yesterday, there's other avenues of where we could use these sensing technologies, which include grading and sorting, packaging, temperature control, drying, refrigeration, and so on. So the world really, at the end of the day, is the limit. But of course, we have the good, the bad, and the ugly. And that's what I mean by you being able to decide what is good for you, which technologies are appropriate, and ask the question at the end of the day, what do I need, and what is helpful out there, or what needs to be developed. A nice statistic that I have here is the startup statistics, or startup company statistics. And I won't go in detail, but I summarized this here, and it says, after most recent recession began in 2007, Establishment birth experienced the steepest decline in the history of the series. The downward trend reversed in early 2010, and establishment's birth have since returned to pre-recession levels, and they're going even higher. So as end users of technology, you're receiving the pressure where these startup companies, of which some are legitimate and some are not, are offering products, technological products that seem to make your world a much better place. But you need to ask yourself, really, is this technology accurate enough for me to use? Is this technology helpful? And how accessible, how robust it is long term? And be a little bit, strict with the questions that you're making. Really, if you're telling me that that's going to save me 50% energy, how is it going to do it? Demonstrate it, do it with numbers. And if that information is not available, that's where we come and you can express your needs to us. So I've divided my talk in technology used in the environment, also, some new technology in the ripening rooms, which I basically touched yesterday a little bit more. We have packaging, ripening, non-destructive quality assessment. And each of these talks could be a completely different talk. So I'll just briefly go through all of them. So let's start with environment. Environment, yesterday I briefly talked about for example, the variable speed drives and fans, and how those can potentially help us save some energy. If we've achieved, for example, and if we have the right monitoring of our environment, we can reduce the speed of the fans and therefore save some energy. We have controllers, improvised or optimized controllers can help us as well. Refrigeration systems, newer and more efficient, highly efficient refrigeration systems as well. There's a high research in that field. And then in sensing technologies, of course, sensors like we discussed yesterday, there's temperature sensors, relative humidity, electronic odor or electronic noise, like they call, color and near infrared, and I'll try to go through each of them briefly. So this is one refrigerated system that has caught my eye. It's called an ice battery. And why is it called an ice battery? It's typically a cold or a heat is stored in these batteries when it's not needed, let's say during the night. When you do not need heat, you can keep when you do not need cold, you can keep ice in these batteries, and as you need them during the day, you can pump air through that ice and distribute it through the refrigeration room. In some cases, if you, comparatively speaking with traditional systems, you can reduce the energy consumption by exponentially. In this case, for example, this analog to a battery, as I said in this schematic, analog to an ice battery. If we turn off the compressors and cools with stored ice, we can cool up to 6 hours without the need of additional energy. I mean, this confined ice can be kept effectively in those conditions to be able to, even though it's required energy to produce, it's the dissipation of heat or the loss of heat in these chambers or in these batteries, it's much more efficient. So you can typically enhance the energy consumption or reduce the energy consumption. This is just a small example. Of course, it's not the case in every case. There's many factors to consider, but this is typically how a variable frequency driver saves us money. So, and let's say a fan running at half speed consumes around 1/8 of the energy compared to one running at full speed. So if we're running at full speed, we're spending much more money, much more energy to keep it running. In this example, 80% of the nominal flow, power consumption is reduced by around 50% when using a variable speed drive. And variable speed drives are, there's multiple types. There's AC type drivers, motors for optimization. There's many ways of developing or having access to variable speed drivers, and this behave differently and can save you energy at different levels. Of course, the overall design of the ripening room, as we discussed, better development of the room, better controllers. They can control the levels of CO2, have even oxygen sensors, CO2 sensors, ethylene sensors, temperature, relative humidity sensors, everything embedded in the controllers that we can control the conditions much more effectively than if we do it by hand or if the controllers are not doing the right thing. So for example, in these tarpless ripening rooms, which are the most advanced, you can control ripening much better than a conventional room as we've discussed yesterday. How do temperature sensors work? Let's not put attention to this slide. Basically, very simplistically, a temperature sensor changes either its electrical properties or its electrical properties which are reflected or directly reflected to the changes in temperature. So it's like, imagine an expansion or contraction. And that's what typically is measured. And there's multiple ways. There's thermocouples, thermistors, resistant temperature detectors, and each of them have different accuracy rates, robustness, and so on. So you need to be aware that there's also a difference in pricing, that when you're typically inexpensive temperature sensor is not the best of quality. And of course you can get sensors now, temperature sensors for electric temperature sensors, thermistors for less than $5. But you need to ask yourself, are they robust enough? Are they going to be measuring? Are they can we calibrate them? And so on. This is just some examples. The future is going wireless. That's one thing that I've observed, either Bluetooth, Wi-Fi, whatever technology is out there, everybody wants to handle it from their phones. And really, at the end of the day, would you would have ever imagined that we could have had that power with our phones? Some of you might be able to log into your ripening rooms right now and see how your bananas are ripening, or monitor the environmental conditions. That can be done. And that is the future, or what we're calling the Internet of Things. This is one example of a wireless technology of fairly reasonably priced. Other wireless sensors, of course, from different manufacturers. Handheld temperature sensors as well, where you can communicate really, in this case, it's not like the phone is the temperature itself. The phone is a portal to communicate with the sensor, and then the output can be sent to your phone. So you can monitor temperature in your phone, like we mentioned. Handheld temperature sensor or infrared temperature sensors as well. The technology has advanced, where you can even control what is the type of material that you're trying to monitor and so on. So they are much more, the technology is much more developed now, comparatively speaking, than 15 years ago. Let's talk a little bit about relative humidity sensors. Similar to temperature sensors, they just simply, the characteristics of the sensors vary in relationship to the relative humidity, and typically it's an electric measurement, either current or voltage, changes in voltage, whatever they're measured with this. So again, you can imagine that an inexpensive sensor, they are available, they're probably not as accurate, not as robust as you would like for monitoring purposes. We talked a little bit of psychrometry yesterday. There is commercial psychrometers. In other words, this digital interface would offer different outputs, not only relative humidity, but also temperature, dry bulb temperature, wet bulb temperature potentially, dew point, and other additional measurements that allow us to work with psychrometry or the study of moist air. There's different manufacturers, like the ones that I'm presenting here. And something that is relatively new, which I think has a big potential, is optical fiber relative humidity sensors. Differently to the typical relative humidity sensors, which deal with capacitance or resistance, changes in voltage or current, these sensors have been developed with new nanotechnology particles. And nanotechnology has advanced the development of sensors significantly, and it will continue. I envision it as it will continue to make sensors much more efficient, and other technologies as well. So in this case, this is a silicon-based, oregano silicon-based coating around, or it's adhered to an optical fiber, and that coating changes its properties depending on the relative humidity, and therefore through the optics or through the optical fiber we can detect those changes and they correlate with the different relative humidities. The advantage of the sensors is that, as we can see here in response time, this is just an exhaustive sampling of different types of sensors. We have electronic sensors like the ones that I previously described in green, acoustic sensors in red, and this optic sensors in blue. And as we can see, the response time is significantly higher than compared with others. So it could be done in vivo, in situ, much faster with less energy. Interesting field. There's not a lot of sensors available in the market at the moment, but I would suggest to keep your eyes open. This is technology is going to continue to evolve. Odor, or basically odor or smells or electrical noise have been suggested as an alternative to look at quality, look at ripening. The world is the limit really at the end of the day with odor. Some have been successful and some not. For example, this Xenos, I do not believe that it is commercially available anymore, except if somebody, it is not. So this is one of the technologies that I wanted to incorporate here, that, even though they've been commercially available, probably due to pricing, availability, others, it wasn't successful in the market. So there is technologies available that might be able to be helpful, but there's many factors that we need to consider. And that's what I mean by we need to make the right questions. This is just some notes and cost, different manufacturers for the sensors that I mentioned previously, and I'll include that in your package so that you can have access to it. Let's talk a little bit more of packaging. The packaging technologies are changing as we speak, especially due to nanomaterials. Nanotechnology hasn't only improved sensing technologies, but I think that it mainly has improved packaging technologies. And something as simple as microperforation packaging, headspace sensors can help us both evaluate and use those packaging much more effectively. This is just an example from a different field. We have, for example, this titanium oxide bottle, which is inexpensive to make, and it's mainly used in the dairy industry as it protects the integrity of the product and many other factors. This nanoclay, for example, has got a darker film attached to it, which selects the wavelength of light that can go into your product, and therefore it keeps it longer, it keeps a better quality, it reduces oxidation and so on. So nanotechnology is important. Hygroscopic salts or hygroscopic beads, especially with dry commodities, are also growing. Basically, you want to avoid that condensation. A perfect example is mushrooms. Mushrooms have a high transpiration, high respiration rate, and due to that, you see a lot of condensation in the majority of the packages. So either through hygroscopic salts, you can control that condensate, or by developing permeable films, you can select certain gases, including the water molecule, to be removed while keeping the safety and the quality of the product. Nanomaterials is something as simple like a conventional product, or this Toyo Lotus product, which is embedded with some nanomaterials that avoid this yogurt or whatever to stick to the surface of the top. So it's just for quality. and that's ongoing and changing. Micro perforations through specific equipment that can be installed online, and packaging equipment. They create micro perforations in the packages that allow a good, appropriate gas exchange. One industry that has benefit from this is the bread industry. I see this growing even more now in the US. A lot of places where you go, you see this little perforated bag, and it basically keeps the bread fresher, much softer. It doesn't, the humidity is not, there's no condensate inside of it, so it's a pretty nice option that could potentially be evaluated and used in fruits as well. Headspace sensors, we have quite a bit, even in display out here, where basically we are detecting oxygen levels, CO2 levels, conditions of the packaging. In this case, this is a headspace sensor for different gases being analyzed in the packages. We have other headspace sensors for oxygen and so on. And this is just some pricing of as well, or some summarizing. I won't talk about the ethylene sensors right now and CO2 sensors, as I've included in the next section in ripening. We have, of course, like we know, there's many aspects that could be measured or need to be measured while fruits are being ripened. We have ethylene production and sensors, of course, for ethylene detection, CO2, O2, and other gas detections. 1-MCP as well, or the production of 1-MCP, as you've learned right now. So I don't need to go in much depth here, but we have a representative as well, where we have this catalytic generators for ethylene. Alternatives, of course, of ethylene sources, like we talked yesterday, and they, of course, vary in price depending on the sensors. As electronics improve, there's also inexpensive ethylene sensors that could be installed with any data loggers and can potentially have high accuracy and sensitivity as the one described here. Probably the gas detection in the range is not optimum, but it can be used as well. Other ethylene sensors, as probably you've seen even out here, including this Felix instrument for ethylene detection. New technologies in this field. There was a group in MIT researchers that, with the objective of continuing with the Internet of Things, which I believe is the future, and you'll see much more of that, is they were trying to develop a wireless ethylene detection method, which is not currently commercially available. But I do see this as not only with ethylene, but other gases and other environmental condition measurements also going wireless. There's a lot of efforts in both in the academic and in the industry fields going for this. Unpackaged sensors or sensing, I think that they've been previously mentioned. Some are temperature sensitive. Some claim to be able to monitor or reflect how ripe the product is. I don't know how realistic that is. I have not evaluated it. Probably indirectly it can do it. How accurate it is, I wouldn't say it's very accurate, but it might. So, and again, with the evolution of nanotechnology, this will continue to change as well. Ethylene sensors are important, so I did include an exhaustive list or a larger list here of different prices and so on that you can access, starting with the inexpensive Kitagawa tubes, as I mentioned yesterday, up to gas chromatographers, which would be the much more accurate but much more expensive. CO2 sensors, we did talk about them a little bit yesterday. Again, they're trying to go wireless, different prices, different qualities, as we described. And they can be, embedded in your ripening system, in your data acquisition system, or whatever. Oxygen sensors as well, which are broadly used, oxygen and CO2 sensors. And probably Florence can help us here as well. They claim that there's taste sensors for different qualities of fruits, and how, again, Does this really correlate with how the panels perceive the different taste? All the questions that we need to ask, and how useful or how helpful would be for you to have a sensor of this sort, detecting taste or simulating taste, human taste. Gas detection, oxygen levels control, also absorbers of oxygen. They claim that also absorbers of CO2, ethylene, and so on, which includes one MCP. I'm not going to go in depth much of what MCP is because you guys already discussed and learned all this. But you basically buy the packages where you can treat your fruits accordingly. There's just different prices here of either 1 MCP, gas sensors, ethylene production, and so on. And the last but not least is, how are you going to detect quality? This is a typical packaging unit operation, or coming from the field all the way to the cooling and storage. You can think in probably multiple sections where you are or would like to monitor quality, ripening, or how ripe a product is. One of them is in the field. So it would be ideal to have a portable unit where we can detect quality attributes or ripening in the field. But there's also in the line, before you're even ripening or after ripening, if you want to resort. Typically it's been done through hand sorting, but as technology evolves, electronic sensing and sorting is also changing, and you're going to see a lot of other sensing technologies that will be incorporated in the line that are able to detect more features of interest. But how does this electronic digital sorters work? Basically, you have a mix of products, different ripenings, stages, and so on. And basically, we have sensors that can sort them into good, bad, different ripening levels, and so on. Typically, how they work is either through color, or now there's cameras, near-infrared cameras, infrared imaging, and other technologies that are evolving, and they're hopefully going to be available in the next 20 to 25 years. So as we know, I'm not going to go in depth here, but light interacts differently with the product depending on their chemical attributes, depending on their color, and so on. And that's when you use different color imaging techniques to be able to detect surface changes automatically. Near-infrared imaging, or different spectrums of light, interacts differently with the produce to give different quality attributes. And near-infrared hyperspectral imaging systems that are online, of which one distributor is out here. But again, the question, calibration. This company here, SCIO, by Customer Physics, claims that they have a refractometer that is around $400 with the a license that can detect the quality of products. So if you look at this, you have to question, is this real? How can we prove that this is real, and how can this be helpful? And of course, there's other hyperspectral imaging that is being incorporated into the lines right now, and they can potentially develop into newer systems that are portable, as the ones that I'm showing here. This is just an example of currently how hyperspectral imaging or near-infrared imaging is being used in the field. Key Technologies company can sort for different sugar levels of potatoes, for example, which is the quality attributes in processing potatoes. We have color images, hyperspectral images to detect the presence of fiber tissue, and spectroscopy as well. This is computer tomography and X-ray for other quality attributes. Currently not commercially available, at least the computer tomography, but X-rays are. And computer tomography will continue to be used in the industry, and hopefully there'll be a development of a system that is fast enough to be used online and so on. MRI as well, similar to computer tomography. Here we have just different industry representatives. We talked a little bit about this yesterday, and some commercially available equipment in the case of sensing technologies. So I'm out of time. Thank you very much, and I'm open to questions.